Ladies and gentlemen, one of the critical assumptions of regression, which you got to check whether it's violated or not, is known as the heteroscedasticity assumption. And before we do that, I want to take you back to something you already know. This is a linear regression line, and there's a gap between. The line is called a fitted line. That line is a predicted line. It is a predicted value of y. It's a value of y that you have to note, okay? It's a value of y that you have to note. But then the observation is down here. The observed value is down there. So it means that it is not on the line. And so it is far away from its predicted value. The predicted value is there. The gap between the predicted value and the observation is the residual. The residual is the unobserved error, the disturbance time, the systematic noise. Okay, sometimes we call it the idiosyncratic noise, random noise, stochastic noise, all of that, those terminologies. The residuals appear to be one of the interesting things in a regression because it is the unexplained part, it is that part of the regression that you don't observe, so you are not able to use it to explain the behavior. And you got to check and be sure that the residuals are having two characteristics. One, the residuals must be zero on average. That's why we say the expected value of the error term should be zero. So the residuals on average should be zero. Two, the residuals must be constant. Okay, we proved this using the variance covariance matrix, but I will dissect it further for us. Every multivariate regression, like what you see on your screen, every one of them, okay, has a residual. And that when you estimate the model, you expect the residuals to bounce to zero. Heteroscedasticity comes from the Greek word hetero, which means different. And it comes from skedastic, which means spread. Indeed, somebody was talking about dispersion, okay? How nucleated or how dispersed the data plots are. Now, this spread is measured by the variance. And the square root of the variance is the standard deviation. You know that. Now, this word heteroscedasticity is the longest 18 words in the world of econometrics. So it's an important word, at least it's the longest. It occurs when the variance of the error term given, and this is important, given the independent variables is constant. Sorry, it's not constant. Now, when I say it's not constant, it's very important. Now, it is not constant means there is an I attached to the sigma square. It is constant means there is no I attached to the sigma square. So please note, when the variance of the error term is constant, that is no I, it is homoscedastic. But when it is not constant, with I rather, then it is heteroscedastic. So the heteroscedasticity is defined as the variance of the error term given the independent variable being, sigma square I. It occurs because there are omitted variables, because the model has not been properly specified, because there is some data mistransformation, outliers, influences, and even multicollinearity that we have discussed. All of these can cause the variance not to be constant. But what do we mean? What do we really mean by the variance not constant? Come on, let's get deeper. First of all, homoscedasticity or constant variance is needed if you want to justify the T statistic, the F statistic, the NM test, and the confidence interval for OLE. You need homoscedasticity. When variances are heteroscedastic, the OLS estimators are still linear, unbiased, consistent, which means that the R square is good. You still have a high R square, but it is no longer best. It's no longer efficient. And what does that mean? It means that it does not have the minimum variance. Now, the variance should not be too big. The variance is not minimum, but you need to have minimum variance. A modicum of variance is accepted, but it doesn't. So it no longer blue, best linear unbiased estimator. The standard errors, not a beta statistic. Please note the beta parameters will not be different. It will still remain as it was, but the standard errors become overestimated, and hence the p-values and all other tests, wall tests, confidence interval, all of them become biased. Invalidity is, impregnated, leading to misleading conclusions in the results. It can even cause type 1 error. So it's very important to check for heteroscedasticity and correct it. Caution. Heteroscedasticity has never been a reason to throw away an otherwise good model, according to Mankiw. So what it means is that the fact that there is heteroscedasticity also doesn't mean that your entire model is balderdash. No. Graphically, we can use residual plots to plot the errors. Okay, we can do that. Okay, on the axis against the predicted. The residuals must be unbiased. Now, I'm going to tell you this is very important because it will cut across other things. The residuals must be unbiased. What does that mean? What it means is that they must have a zero mean. So when we say an unbiased residuals, it means the mean is zero, which is what we're expecting. Hallelujah. It means zero. In any thin vertical strip, okay, or any vertical rectangle in the residual plot, the mean must be having a zero mean. The errors must have a zero mean. Now, so that's what we mean by unbiased. Keep that in mind. When we say it is homoscedastic, it means that it must have the same stretch. The spread of the error should be in the same, or should be the same in any thin vertical strip. I'm going to give you examples, and I'll rather do a test. That's why I'm going through this. So, which one is heteroscedastic and which one is homoscedastic? On this graph, the data on the left, the data on the right, which is heteroscedastic? When you check it, which one is heteroscedastic? Heteroscedastic. Is it the R1, the one on the right, or L, the one on the left? Which one is hetero? Heteroscedastic, right or left? Right. Right, exactly. Right. R-I-G-H-T, right. Okay, so the one on this right side, this is heteroscedastic. This one here is heteroscedastic. Why? Who can tell me why? Because it's one thing seeing it and saying that it's heteroscedastic and not understanding the why. The why is important. Who can tell me the why? The why. Why do you say it's heteroscedastic? Okay, so let's see whether Roxanne has got something to share with us.
Why?
Doc. Why, Roxanne?
Doc, I think the stretch is not uniform.
Good. Yeah. The stretch is not uniform. I like that. I like that. So the spread, it is spreading, but the gap between each other is not constant. Okay, the gaps, what do you see about the gap? You see the gaps were closed at this end portion there. The gaps were closed. The gaps were closed. The gaps were closed. They were tied to each other. The gap, I'm not talking about the items, I'm talking about the gap. It's still 3 elements. It's still 3 elements, but the gaps were closed. But as you go, the gaps are extending. They are getting bigger. The gaps are getting bigger. The gaps are getting bigger. And so it becomes heteroscedastic. That's the point. Now hold on. Look at this. I have 6 situations here. And I want to really, really test your brain, because this was one way that will really indicate that you have been following from the very beginning of this course. So open your mind and tell me clearly what is really happening here. If you look at the first one, okay, here, it is unbiased and it is homoscedastic. Who can tell me why? It is unbiased and it is homoscedastic. Why? Why is it unbiased and homoscedastic? There's so much noise around. So I decided to.
The individual.
No, I'm not talking about the variance. I want to know first, why are the errors, the residuals, said to be unbiased here? We'll come to the variance, but the residuals, why can we say that in this A and in this D, the residuals are unbiased?
Yeah, because the expectation of it will be 0.
Why would you, what graphically proves that? That's my question.
Because if you look at the upper and then upper of the graph and the lower, it looks like they are even distributed, so the summation will be 0.
It looks like they are what?
They are even distributed, and the upper and then the down. They move.
So this one here, are they not even distributed? The one in B here.
They are not, because it changes with the observations.
It changes with the observation.
Yeah.
How does it change? So this one is not changing with the observation, the one in D.
Okay, I get it.
I'm only making you guys think. Edward. Edward, yes.
Okay, Prof. Let me just use the pictorial observation, and it looked like if you compare it to the bias, the observations move in a particular pattern, either from the bottom, upper right, or the opposite. But this one, the unbiased, they are just scattered all over the place. Even
Are you sure?
Even with the D, you will see that the observations, some are coming down and others are going up at the same time, as compared to the biased ones.
No, but if you look at the D and the E, they are similar. Do you realize that the D and the E are also getting similar?
Yeah, but you can see that it follows a pattern where they are all going to the upper right.
They are all going to the upper right.
Yes.
But the E, they are all not going to the upper right.
Yeah, I'm talking about the E. The D, some are coming down, others are going up at the same time, sort of.
All right, okay. Thank you. Thank you very much. That is interesting. So, ladies and gentlemen, so here's the thing. You need to be able to detect unbiasedness from biopsy, because this thing took me some time to crack my head around it. Yeah. So here's the thing. If you look at the data plots here, if you take the data above the line and then the data below the line, it is like a mirror image of it. I want to repeat that. It is like a mirror image of it. The information content above and the information content below the line is like a mirror image, unbiasedness. The same thing, when you look at the D, it is like a mirror image. The one below the red line and the data above the red line is like a mirror image of itself. Now, when you look at the E, it's not. Because if it was, the information here must be plenty equally like the information up there. But when you look at this, if you look at this information, the information here, okay, if I should draw a kind of a curve around this, okay, so this one must also be moving towards a curve around that for it to be like what? Like a mirror image. But it's not like that. Okay. Now, when you go to this one, it appears that it is, but it's not, because when you look at the information here, while this one is going up to this level, this one should have gone from here, okay, up to that level for it to look like what? A mirror image. Okay, so it is when it is depicting that mirror imaging, then we say the data is unbiased. I know someone on this hand is up. Minta, your hand is up. Maybe you want to say something. So that is that. I want you to understand this unbiasedness very, very well. Okay. Then we can proceed. Now we've not come to the variance. As for the variance, it's obvious. Okay. As for the variance, it's obvious in there. All right. So that is unbiased. Now let's go to the variance. By the way, everything we've said here is here. So the use average to 0 in each thin vertical strip. Okay. And now let's go to the variance. Now this variance is homoscedastic because the gaps, not now the observation, is no longer about observation, but the gap between the observations appear to be constant. Okay. So let's say this gap here between this and that. Let me just take these two. Okay. If you see the gap between these two, it appears to be a similar gap between every other ones, generally speaking. Again, that one too is general, is the average of the spread. It's not just the average, but the average of the dispersion is constant. Okay. Now the same thing with this, the gap between the observations, okay, is constant. Okay. The gap between observations relative to the regression line is constant. But let me just go back here. When you look at these ones, okay, it appears, you see, when there is a pattern, okay, when there is a pattern being shown there, it is homoscedastic. There's no doubt about that. When there is a pattern, okay, it is showing some homoscedasticity. But when there appears to be no clear-cut pattern, and when we say no clear-cut pattern, remember where the regression line is, where the residual line is. Because the residual line is what is indicating whether or not there is a pattern, okay? So it appears that here, the entire data set is not, there seems to be not a pattern, okay? It looks like when one, if you look at this, let me put the line around this, okay? We can see that when you are here, there's a negative relationship here. And then when you take it from this angle there, there's also a positive relationship there. Okay. The pattern is not clear. As you move from the left to the right, the pattern is not clear. As you move from the left to the right, it looks like some are rising, some are falling, and some are falling, some are rising. That is heteroscedastic. Okay. So the spread is not constant. Now, the same thing, when you look at this, okay, the spread is constant. Okay. The spread is constant. As you keep going, you can see that the gap between them, the spread is constant. But here you can see that the gap is increasing. The gap is increasing. The gap is increasing. The spread is increasing. Okay, here the spread is increasing as you move along. The spread is increasing. Sometimes it's even falling, but the spread is increasing. The gaps are increasing. The gaps are increasing and falling here. And that is it. So it appears that the pattern is not obvious. And that is a point being shown here. Okay, so the key point is that when the standard deviation, when there's a standard deviation is small, if you look at like the D1, okay, the D here, the standard deviation is very small at the edge to the left of the plot and large to the right, okay? So that shows that the mu's are heteroscedastic, okay? The errors are heteroscedastic. This point is an important point. So it's very, very important to get it, okay? So you can see that we are rising, we are falling. The most important thing is that when you are able to detect the gaps between the residuals, okay? When you're able to have increasing gaps or decreasing gaps, then you are now moving towards the heteroscedastic world, okay? Then you're moving towards the heteroscedastic. Sometimes it's not clear when you use graphicals to show, okay? So we'll get a proper check, and the proper check is by using what? Wow. The proper check is by using statistics. And so we're going to use some statistics to check that. And one of them is detecting heteroscedasticity graphically. Okay. So we're going to use this graph, par inflow graph, to show it. And you guys have seen it already. Okay. And then we shall use plot gene multigraph to show it. And you see that it will give a sense of non-normality, non-linearity, and all of that, which we indicated. You can see this. Let me just go and run the par inflow command again. In fact, this is not the main thing, but I just want to run that to just, you know, remind you guys of where we were. Okay, so it's called plot gene multi. What is that? Okay, plot gene multi. We had it somewhere. There you go. Okay, so this was plot gene multi. This was a graph we had. Oops. Let me just go back. So this is it, plot gene multi. Okay, and you can see, this will help you to see the heteroscedasticity a little bit, not much, but a little bit. Okay, so the first one is a residual versus a fitted plot. Okay, it is up and down, or a rise and fall variance. So it's not just horizontal. Okay, so it shows a bit of nonlinearity there. Okay, this one, it shows a bit of nonlinearity there. Curvature with the residuals. The KQ plot appears to show some bit of non-normality. If you look at the scale location, again, it shows some rise and fall of the variance, okay, which can exhibit some non-linearity. So this is graphical. All right. So let's go to, you see, graphical is good, but graphical, you can't be certain of it, especially when the graph is not clear. So it's good to have certainty. And that is why we need to test for heteroscedasticity. There are several tests, actually. There are several tests of dealing with heteroscedasticity. Okay. One of them is PAC-LM test. And that PAC-LM test, what it does is that the residuals, you take the log of the residuals, and then you take the log of every other thing. Okay, every other independent variable, PAC-LM test. Okay, the Glycide-LM test, what you do is that you take the estimated residuals, and then you take the absolute value of that, and you regress that on the independent variables. Okay, then they have the Goffrey test. You take the log of the squared residuals, you regress that, and then it's just a way of changing each one of them slightly. The Goffred and Quant test is for cross-section, it's not for panel data. So note that. Big and Goffred test. Okay, so that one you take the square of the residual, not the absolute value, you regress that on the independent variable. The White test, you take a square of the residuals and you regress that on the independent variables and a square of some of the independent variables. And the interaction, this is the interaction of some of the independent variable. So squares, okay, this one has gained popularity, the white test. Okay, so you're taking care of all things, okay, to address the heteroscedasticity. And then the KB test, you take a square of the residuals, then you regress that on the dependent variable square. Okay, and that. So what is a hypothesis? The hypothesis always says that those coefficients, okay, there's no difference across them. There's no difference in the deltas. That's what it's indicating. But then the alternative says at least one of them differs. Okay, so at least one of the independent variables, affect the variance of the errors. If one of the independent variables affect because when we were defining homoscedasticity, we defined it as giving the independent variable. But now, if it's no longer given, but it's rather affecting the error, then it means that we have heteroscedasticity. The decision rule is to reject the null hypothesis, okay, if the LM test which is the test statistic, it is n multiplied by the R square. Okay. If that statistic is greater than the chi-square degrees of freedom, and then you conclude that there's a significant evidence of heteroscedasticity. If you reject the p-value, this is the most important one. If you reject the null hypothesis, you will reject it if the p-value is less than 5%. Okay, so if you reject the null of homoscedasticity, then you are concluding that there is heteroscedasticity because the p-value is less than 5%. So the key point is that we want the p-value to be greater than 5% for homoscedasticity to happen. That's it. That's the key point. All right. So how do we use the test? Well, one test we use is the BP test function, okay, from the LM package. We install that and then we use that to carry out the white test. So you can see that there were several tests, but I want to use the white test. So you do this library package, install it first, and then use this BP test gen multi. Okay. Let's run that very quickly in our result. Let's run that very quickly in our result. And so we just go to our command and we type that very command. Okay. And what is the command? This is a command. The command is BP gen multi. Of course, I have already loaded the library test, LM test. Okay. So I do that. Okay, let me load it again. So you run this command and there you go, the p-value, watch it here. This is a studentized Bruch-Pagan test, okay? And then you can see that the Bruch-Pagan test statistic is 31.8. That's what you put in the journal article, okay? With the degrees of freedom of 8, the p-value is 0, okay? The p-value is basically 0. What does that mean? It's less than 5%, okay? So we are concluding that heteroscedasticity is present. That's what it means. The p-value is less than 5%. So let me just take you back to the note. So we conclude that heteroscedasticity is present, which means that the standard errors will be unreliable. To be unreliable. Now, let's prove that with another test, the Goldfeld and Korn test. That one assumes that the data is already ordered. So it splits the sample in the middle without omitting any central observation. This command with our data set will handle that. Let's run this command. Okay, and I want to do this last one. And when you do that, run the test command, you are also going to get a p-value which is exactly 5%. Okay, a p-value that is exactly 5%. That is interesting. Okay, where you have a p-value that is exactly 5%. Now, I'm going to do another few tests, and I just want to show you something here, okay, because I'm concluding this. So you can use these other tests. There's a package called Library Scedastic. Library Scedastic. You can load that package and use a white LM test for our data. It will give you a p-value which is also 0. again, heteroscedastic. You can do the Goldfeld-Quandt test for that package, the Bridge-Pagan test for that package, the Cook-Weisberg test for that package. Okay, almost all of them are going to give you that there is heteroscedasticity. So our data, our analysis is exhibiting some form of heteroscedasticity. Now, there are more tests you can do to correct and check that. So you can go and check all of these, the Gleiger test, and library OLSRR also has some interesting tests you can check, okay? And in fact, I will just do one final of these just to let you know how they will look like if you should go and do them. So when I load this and you look down here, okay, you will see that the p-value here is 0 again. If you do the COVID, you see the p-value here is 5. But this one is 50%. Okay. If you do the Bridge-Pagan, is 0. If you do the Cook-Weisberg, that is 6%. If you do the Gleiger, that is 0. Okay. And then you come for other ones like this, they are all exhibiting almost 0. P-value is almost 5%, 6%, 0, 5%. This is 0. And then this one is also 0. So basically, there appears to be some heteroscedasticity in our regression. Now, what does this mean? This means that, yes, there may be some problems. So how do we handle that? Next time, we're going to learn how to handle heteroscedasticity inside the regression. Ladies and gentlemen, that brings us to the end of the entire